Every type of bridge offers an economically optimal range of spans. For an arch bridge, this optimal range of spans is between 60 and 300 meters. A suspension bridge is efficient for spans between 300 and 1500 meters. Cable-stayed bridges generally have spans between 80 and 500 meters. Box girder bridges are used up to a span of about 150 meters. Continuous plate girder bridges are efficient up to 150 meters. A simply supported plate girder railway bridge is economical in the range up to 30 meters. Distinction must be made between a deck girder bridge and a through girder bridge. Three deck types are common: the open deck steel grid, the orthotropic deck, and the composite deck construction. The plate girder bridge is the structure considered in this program. Plate girder bridges comprise the main girders, the cross girders, the stringers, or, in case of a railway bridge, the rail bearers, and finally the deck. First, a railway bridge is considered. The following components and concepts characterize this type of bridge: the clearance gauge. Fixed objects are not allowed inside this profile. The check rail, a beam parallel to the rails, serving as a guide for the train in case of derailment and protecting the load-carrying structural elements against severe damage. The inspection path, the floor between main girder and rails, permitting the inspection of the track and the bridge. And the footway and cycle track, situated outside the main girder, making it possible to cross the bridge without interference with the railway traffic. Components of a highway bridge are the crash barrier, the marginal strip, two lanes, the hard shoulder, and an inspection path between crash barrier and parapet. In this case, the clearance gauge is of minor importance as there is no upper bound. Two important concepts for all types of bridges are the span, the distance between the centers of the supports, and the construction depth, the distance between the top of the deck or rail and the lowest point of the bridge cross-section, including splice plates and bolt heads. The essential function of a bridge is to transmit the various loadings to the supports. A vertical concentrated load on the deck is supposed to be transmitted to the stringers and from there to the cross girders, the main girders, and finally to the supports. Large lateral displacement may occur due to wind loading. Here, the main girders are loaded by bending along their weak axis. Lateral rigidity of the bridge is not adequately guaranteed. This rigidity can be achieved by means of a bracing system. Diagonals are inserted between cross girders and main girders to constitute a rigid truss. Here, the stringers are omitted for reasons of clarity. the equally distributed wind loading is replaced by an equivalent set of concentrated loads acting on the joints of the wind bracing. These forces can now be transmitted to the supports. The wind bracing can best be observed in a railway bridge. The effect of wind loading can be rather dramatic. In this particular situation, even leading to destruction. Braking and traction forces act in the horizontal plane in the direction parallel to the bridge axis. This causes bending moments with respect to the weak axis in the cross girders. As the cross girder to main girder connection may be considered to be a hinge, large deflections might occur if not prevented by bracing. If this bracing is used, it must be situated in the middle of the bridge. The bracing and traction forces are transmitted to the stringers, the rigid truss, the main girders, and then to the supports. A wheel may exert transverse forces on a rail and rail bearer. These horizontal forces cause bending of the rail bearer with respect to the weak axis. Again, a bracing is applied to protect the rail bearer against too much deflection. This bracing lends horizontal stiffness to the rail bearers. Moreover, it fixes the distance between the rails. The bracing for braking and traction forces is located at the same level, preferably situated as near to the rail as possible. The horizontal forces are transmitted to the cross girders and via the wind bracing to the supports. In a composite steel and concrete highway bridge, and bridges with an orthotropic deck, the deck serves as a bracing for all horizontal forces. In a composite structure, formwork is needed during erection. When the concrete deck has reached sufficient rigidity, this formwork may be removed and the deck acts as a rigid plate. The lateral forces are mainly transmitted to the end cross girders and then to the supports. Each color in this computer picture represents a certain interval of shear stress due to horizontal wind loading. It shows that the stress distribution at the end cross girder can approximately be represented by a straight line. An important concept is the U-frame stiffness, in particular at the supports of a deck girder bridge. Due to the horizontal wind loading, the lower part of the web may suffer large deflections. Vertical forces at the support, which cause compression in the web, might lead to instability. By inserting brackets, horizontal forces can be transmitted to the supports, avoiding large deflections. They also distribute the reaction forces into the web. Instability is thus avoided. Also, in a random cross-section, stiffness problems may arise. Stiffeners between cross girder and main girder guarantee rigidity. They limit the displacements and vibrations due to wind and live loads, and damage caused by collisions. The bending moment in the main girder caused by vertical loading introduces compression in the upper flange and might lead to buckling. The end portals, composed of end cross girders, brackets, and the main girder, are usually constructed with extra stiffness so as to fix the upper flange. Without intermediate U-frame stiffeners, the buckling length would be equal to the span of the bridge, resulting in very low ultimate stresses. By inserting intermediate U-frame brackets, the upper flange is rigidly connected to the cross girders. This creates nodal points. The buckling length is the distance between two nodal points. Thus, the buckling length is reduced to the distance between the cross girders. A panel of the main girder is limited by the upper and lower flange of the main girder and two cross girders. A test on such a panel in pure bending. Buckling of the web in the central panel occurs including local flange buckling in the final stage. The same test in shear in an end panel. Solutions of the plate buckling problem are available for simple, though important, geometrical situations. Here, only a short outline is given of a rectangular plate hinged at the supporting edges, with loads distributed along two edges, including shear stress. Regarding the geometry, two parameters are introduced. The aspect ratio, alpha equals A over B. The Euler buckling stress, sigma E of a strip, length B, width unity, and plate thickness T. Regarding the stress distribution, two further parameters are introduced. The stress ratio psi equals sigma 1 over sigma 2, and the equivalent stress, sigma V. Depending on alpha and psi, the buckling coefficients K sigma and K tau are determined from a set of curves. We now find two parameters, sigma x and tau x. Depending on the parameters determined previously, an interaction formula gives the equivalent buckling stress, sigma IV. A relative slenderness ratio, bar lambda, follows from the square root of the yield stress over the equivalent buckling stress. From the plate buckling curve, we find the buckling stress, sigma B. By a factor C ranging between 1.33 and 1.70, a correction on the safety factor is introduced. C equals 1.33 belongs to the extreme situation of plate buckling due to pure bending. C equals 1.70 belongs to the other extreme situation in which plate buckling is very much comparable with buckling of a bar. Reality lies between these two extremes. The final condition is now C multiplied by sigma V is smaller than or equal to sigma B. If B over T, flange width over flange thickness, is large, the flange buckles locally. However, such a flange offers great resistance to overall buckling. A small B over T ratio encourages overall buckling and reduces the tendency to local buckling. Clearly, these two buckling modes create conflicting requirements. This problem can usually be solved by choosing the optimum B over T ratio. Neither buckling modes occur if the compression flange is rigidly connected to the concrete deck of a composite structure. Live load is always multiplied by an impact factor greater than 1 and becoming smaller with increasing span. Moreover, in motorway bridges, the loading is multiplied by a factor equal to or smaller than 1, representing the probability that the bridge will ever carry full loading. Loads are carried by I-beams, which can be welded or rolled. The rolled sections can be tailor-made. At Arbet in Luxembourg, a well-known process is applied: quenching and tempering. It's here for the first time that this process is applied on a large scale during the rolling of the sections. The effect of local quenching is clearly visible as a dark strip at the section flange. In this way, strength and quality of the material are improved. Rolled sections are usual for rail bearers and stringers. Cross girders are sometimes rolled, sometimes welded. The main girder is usually welded. Connections can either be welded or carried out using high-strength friction grip bolts. Interesting is a connection, axially loaded in tension. Consider this well-known symmetrical situation. The path followed by the axial forces is mainly through the bolts. Now, a steel strip is placed between the structural components. The contact pressure between the flanges, produced by tightening of the bolts, is concentrated in the strip. The axial force is now transmitted through this connection by reducing the strip contact pressure. The bolts remain statically stressed and fatigue is avoided. If flanges have become curved due to welding, this concept also applies. The contact surface is automatically located in the center of the connection. From a fatigue point of view, a favorable situation. Stringers can be placed on top of the cross girder, or the upper flange of stringer and cross girder may be kept at one level using the continuous beam connection. In both cases, the stringer can transmit bending moments and shear forces. Additional stresses in the wind bracing depend largely on the type of bracing. The additional stresses are here defined as stresses due to deflection of the main girder, which is not taken into account in the calculation. A bracing above the neutral axis of the main girder is loaded in compression. A bracing beneath the neutral axis is loaded in tension. Two types of wind bracing are considered more closely regarding wind and additional stresses. First, the Howe system, which is statically indeterminate. Due to wind loading, in each bay, one member will be loaded in compression. The great slenderness makes this member buckle easily, and a statically determinate system is left. Obviously, it is not allowed to place this bracing in a position above the neutral axis of the main girder, unless the members are designed to carry compressive forces. How can these additional forces be calculated? One bay of a bridge is considered. The vertical loading elongates the main girder at the bracing level by D. The wind bracing should follow this deformation completely, as the influence of these components on the total bridge behavior is negligible. The displacement D is compensated by elongation delta of the member of the wind bracing by means of an axial force. A K bracing is a statically determinate truss able to resist forces in both directions. The diagonals are loaded in tension as well as in compression, so the bracing level is of minor importance. The cross girder has to follow the deformations by bending with respect to the weak axis. As an axially loaded member is more rigid than if loaded in bending, the deflection D is completely accounted for by bending of the cross girder. Preferably, deformations should lead to bending moments instead of axial stresses. Only 100 Newton are needed to give an I-section member a displacement of 1 millimeter by bending. That is 1 full rotation on the dial gauge. 200,000 Newton are needed to elongate the same member 1 millimeter. Ultimate stresses depend on several factors. Yield stress can be derived from the stress-strain diagram, here produced for a test specimen made of steel Fe E235, approximately equivalent to grade 43 steel to BS 4360. Note the great elongation before rupture occurs. In comparison, the stress-strain diagram is also shown for steel Fe E355, approximately equivalent to grade 50 steel to BS 4360. Considering fatigue, the stress range and the structural details are of utmost importance. As an example, a welded connection between a stiffener and lower flange is considered. Due to the notch, a stress concentration occurs. This leads to a stress interval, delta sigma, due to live load. The effect of each local situation is accounted for by the choice of an SN curve. The code indicates the curve to be applied. Consideration of strength, fatigue, and stability results in ultimate stresses. The lowest of the 3 values is adopted in design. The essentials of this program. The plate girder bridge comprises the main girders, the cross girders, the stringers, or, in case of a railway bridge, the rail bearers, and finally, the deck. General concepts are the clearance gauge, within which no objects are allowed, the span, the distance between the centers of the supports, the construction depth, the distance between the top of the deck or rail and the lowest point of the bridge cross-section, vertical loading, transmitted to the supports by the different bridge components, horizontal loading, divided into wind loading, traction and braking forces, and lateral impact. Bracings for wind, traction and braking forces, and lateral forces on the rail bearers. Additional stresses in howe and K trusses. And U-frame stiffness. Ultimate stresses depend on the factors yield stress, fatigue, and stability. The different connections can be constructed by using high-strength friction grip bolts. The design of railway bridges, highway bridges, and footpath bridges is prone to ever-changing concepts. To clearly highlight the concepts in plate girder bridge construction, an older type of structure was considered here: the plate girder bridge.